problem. We've got our molecular formula, and we've got two NMR spectra, so we've got both carbon-13 and proton spectra. And the important thing when you have multiple spectra is to use them in an integrated way. In other words, don't just kind of jot down a few things about the C13 and then forget about that while you're looking at the proton spectra. Use what you've learned from the C13 to help you make sense of the proton spectra, and that's the way to approach these kind of problems. So if we start with the carbon-13, you can see that the first thing to notice really is that there are 8 peaks in the spectrum, and yet there are 10 carbons in the molecule. So that's important because we could have expected up to 10 peaks. The fact that we have only 8 tells us that there is some kind of equivalence in the molecule. There are some carbons which are in the same environment as one another, either because there's some symmetry in the molecule or because there is more than one carbon joined to the same other carbon, so that you can get equivalence as a result of the free rotation. So let's just note that point down because that's important. So we've got 8 peaks, but 10 carbons, which means that there is some equivalence in the molecule. So as I say, that could mean symmetry, or we'll see once we get a bit more information what that's likely to be telling us. So the next thing then is to look at the chemical shifts, and your data sheet will tell you that these peaks on the right hand end of the spectrum there are C single bond C. So that means that these come from aliphatic carbons bonded to other carbons, and so we know we've got 3 at least of those. We also have this peak, and that's in a slightly different range, and that's in a C single bond O environment. We can ignore the halogen possibilities because obviously there's no halogen in the formula. So that's important to know. There is only one oxygen in the molecular formula, and so that tells us that it's bonded through a single bond to a carbon there, and that's confirmed by the fact that there is nothing down here where we would get carbonyl carbons, but there's nothing in that part of the spectrum. So when we come to interpreting the proton spectrum, we'll know that we shouldn't be looking for any carbonyl groups because there clearly isn't one. Now here, these peaks, your datasheet will tell you, could either be alkene peaks or they could come from a benzene ring. And in principle, we should consider those to be sort of equally likely possibilities based on the C13. Although the fact that there are 4 of them suggests that we've got a big chunk of the molecule in this kind of environment, and at least at A level, that should give you a hint that it's most likely to be a benzene ring, although we can't be absolutely certain of that. If it is a benzene ring, the fact that there are only 4 peaks would tell us that there's some symmetry in that ring, meaning that although there are 6 carbons, we've got likely 2 pairs in equivalent environments. So we'll just note that down, that could be 2 alkene groups, or indeed more, because remember we've got some symmetry in the molecule, but likely to be a benzene ring like that. is how the data sheet shows it. And if it's a benzene ring, it must have some symmetry. There's only 4 peaks present. A bit clearer. Okay, so that's essentially what the carbon-13 tells us. And so now we're ready to move on to the proton NMR. And what we're going to look for straight away is evidence that will confirm whether or not there's indeed a benzene ring there, because that's generally very easy to spot in the proton spectrum. Okay, so here is the proton spectrum, and the place to look for aromatic peaks, your data sheet will tell you, is around here. In that part of the spectrum, the only other thing that peaks really could be is NHs or OHs, but we know that it can't be those, because apart from anything else, those are split peaks, and remember, NHs and OHs don't split. So that confirms that we have a benzene ring, and more than that, we can look at the areas, the total area of those peaks, to tell us how many things are attached to the benzene ring. In other words, how many substituents there are. If we look at the total of the areas of all of the peaks in the spectrum, they add up to 14, which corresponds to the 14 hydrogens in the molecular formula. So that means that each area unit corresponds to 1 hydrogen, and therefore the fact that we've got a total of 2 from this peak and 2 from that peak means that we have 4 hydrogens altogether attached to the benzene ring. And that's important, because if there are only 4 hydrogens on the ring, it means there must be 2 other things. In other words, there must be 2 substituents on the ring, and that's really important information. So when you have aromatics, always look at the total peak area in that region. Okay, so let's just note that down, that this confirms that we have an aromatic ring. Because we have a hydrogen attached to an aromatic ring, shifts. And the total area is 4. Which means that there are 4 hydrogens on the ring, which means that there are 2 substituents. So if we think back to the carbon-13, remember that there were only 4 carbon environments within this aromatic ring. So that tells us something also about the position of these 2 substituents. So let's just think about that a little bit more. When you have a benzene ring with 2 groups attached to it, those could be arranged essentially in 3 different ways. So you could have a 1,2 or a 1,3 or a 1,4 arrangement of those branches, and we're going to need to know which one of those it is. So the key to that's going to be the fact that there are only 4 different carbon environments, so there is, as we said, some symmetry in the ring. Now how that's going to work is going to depend on knowing whether those 2 substituents are the same as one another or whether they're 2 different groups. And in our case, we know they must be different because there's only 1 oxygen in the molecular formula. So they can't both contain an oxygen, but one of them must, so they've got to be two different groups. So let's just label them X and Y to emphasize that they're different. When you now look at that, you can see what the symmetry implications are going to be. So in the 1,2 case at the top, you can see there just is no symmetry. Because X and Y are different, it destroys any possibility of symmetry. So for that one, we can say no symmetry, and therefore 6 C13 peaks would be expected in the aromatic region. And we don't have that. So that's not our arrangement. In the second case, again, you can look, but you can see that having two different groups X and Y means no symmetry. So again, that can't be our case because we haven't got enough C13 peaks to fit that. So again, we can exclude that one. But when we come to the third case, the 1,4, you can see that we do now have some symmetry. Not across the middle of the ring in the vertical sense, because X is different from Y, but we do have symmetry going up here. Okay, so there's a plane of symmetry right through the middle of the ring like that. And that means that this carbon and this carbon will be equivalent. And likewise, this carbon and this carbon will be equivalent. They'll be different from each other because this one's close to X and this one's close to Y, but we've got two pairs. So we'll have two pairs of equivalent carbons. Meaning that there will only be 4 carbon-13 peaks in the aromatic region. And that is what our situation is. So that fits our spectrum. So what we're now can fairly confidently say we're looking for is a benzene ring with 2 groups in the 1,4 orientation. So let's come. So coming back to the proton spectrum, we can now say that we have a benzene ring confirmed by that shift, area of 4 means that we have 2 substituents, and we can add to that information that the 4 peaks in carbon-13 in the aromatic region means that we have a 1,4 arrangement. So now we have our first chunk of structure that we're fairly confident we need to build on to construct our whole molecule, which means we have this, and those 4 hydrogens are accounted for. One thing that's worth noting is that we haven't talked about the splitting here, and that's because the syllabus states that you are not expected to talk about the splitting for aromatic ring systems. So there's no point spending any time writing about it in your answer. Actually, though, you can see that having 2 doublets there fits this as well, because this hydrogen is going to be split by that one, and not by any other, because obviously there is no hydrogen on the adjacent carbon on that side. So this hydrogen is going to split this one, and this hydrogen is going to split this one, and correspondingly obviously the same thing for the symmetry related ones on the other side. So 2 doublets is exactly what you would expect, but you don't need to write about that because the syllabus says that that's not expected. Okay, so now we have to start working out what's going on with the rest of these peaks so that we can work out what the other 2 substituents are. So let's pick one peak and start from there. So if we choose this one, then it has an area of 3. So we can say that this peak has an area of 3, which means that there are 3 hydrogens. So it's likely to be a methyl group. In fact, it has to be a methyl group because we've used up all our symmetry in the benzene ring, but anyway, likely to be a methyl group. And it has an HCr shift, which means that it's not directly bonded to the benzene ring, but in any case that would have to be the case because it wouldn't be a triplet if it was. So HCr shift doesn't really tell us anything important, but we must still note it down. But what is important is that it's a triplet. So let's note that down, and that remember tells us that there are 2 hydrogens on the adjacent carbon. So based on that, we can now say that we have this kind of structure somewhere in the molecule. So we have a CH2 bonded to a CH3, and that set of protons gives the peak at about 0.9 ppm. Okay, so that's incredibly useful. The question then is, where is the peak from the CH2 here? And scanning through the spectrum, the only place it can be is this peak at about 2.5 ppm, because the other ones are either these aromatic ones, which obviously we've already accounted for, or they have the wrong areas. So the CH2 must be that one. Okay, so we can say that accounts for these 2 hydrogens here at 2.5 ppm. Does that fit? Well, yes it does, because it has an area of 2. So for this one we can say that it has an area of 2. Meaning that you have 2 hydrogens, so that fits with it being a CH2, and it's got splitting into 4, in other words it's a quadruplet. Which means there are 3 hydrogens on the adjacent carbon, which fits with that being a CH3. So this is all good. And the really interesting thing about that is its shift. Because it's between 2 and 3, it could have been next to a carbonyl group, but we know we don't have a carbonyl group in the molecule. So the only possibility is that it's directly next to the benzene ring. So we can say that this one has a benzene ring CH shift. And that's really important because it tells us that the benzene ring is now attached here. So we actually know we have that bit of structure from looking at these two peaks at 0.9 and 2.5 ppm. So now all that remains is to work out what these remaining three peaks are and to use those to put together this bit of structure at the other end of the benzene ring. So again, let's start with the CH3. So this one, we can say has an area 3, which means it's likely to be CH3. We can say that it's got again an HCR shift. It's quite different from the other one, but it's still within that HCR range. So we can note that down, meaning it's just going to be bonded to another carbon. And it's interesting though that this time it's a doublet. So it's attached to a carbon with only one hydrogen on board. Okay, so it's a doublet, which means that there's just one hydrogen on the adjacent carbon. So again, we've got another bit of structure now, which we know is going to take its place over here, but let's put that bit of structure together on its own and then we'll just join them up. So we know we have a CH3 here attached to a CH from the splitting, and we can say that this CH3 is the peak at about 1.5 ppm. Again, we then ask the question, well, where is that CH in the spectrum? So we're looking for a peak with an area of 1. And there are two of those. So there's one here at about 4.1 ppm, and there's one here at about 5.8 ppm. So the question is, which one is it? And of course the splitting tells you, because we know it's next door to a CH3, so it should be split into 4, or possibly even more if there were hydrogens on the other side, but it must be split into at least 4. And you can see that the peak at 5.7 ppm is not split, so it can't be that one. So it must be this peak at 4.1 ppm. So we can say, right, that is the peak at 4.1 ppm. So we've got that bit of structure from looking at those two peaks, but what else can we learn from the 4.1 peak? So let's write down what we know about that. Area is 1, which means that there's just one hydrogen. So that's consistent with the bit of structure we've deduced. It's a quadruplet, meaning that we have an adjacent CH3. Okay, so 3 hydrogens on the adjacent carbon. What about the shift? Well, around 4.1 ppm, the only possibility, given the elements we've got present in the molecule, is that that must have an oxygen attached. So that's an HCO shift. And based on that, we can now add on to our structure that there must be an oxygen attached there. And of course, because oxygen forms 2 bonds, there must be another bond there on the other side of it. So we can deduce that bit of structure. And of course, because carbon forms 4 bonds, there must be also another bond here, so that carbon will have 4 bonds altogether. So we can deduce all of that just from this pair of peaks here. So what does that leave us? Well, it leaves us with this peak at 5.7 ppm. And we know what that is because we've got this information at the top here, which we were given, which is that peak is not seen if D2O is added. And remember, that's the signature of an OH or potentially NH, but obviously in this case it must be an OH peak. What happens with OH peaks is that if you add D2O, the OH is converted chemically into OD, so hydrogen is replaced with heavy hydrogen, and deuterium doesn't give a proton NMR peak. So if you change OH into OD, the OH peak just disappears. So this is an OH peak, which is confirmed by disappearance in D2O. It's also supported by the fact that it's a singlet, because remember, OHs don't split. Okay, so it's a singlet because OHs don't split. And OHs can have pretty much any chemical shift, so we don't really need to comment on that. But that fits in with there being an OH in the molecule, and since we've got an oxygen there, we know there was something attached to it, we can say, oh yeah, that's an OH. And we can note that OH gives the peak at 5.7 ppm. So now all we have to do to complete our structure, because if you add up all the carbons and hydrogens and oxygens, we've accounted for all of them in the molecular formula now. So all we have to do is to join these two fragments together. So we know there was something attached at this point to the ring, and we know that here's our fragment and it's got a point of attachment here because there's a bond unaccounted for there. So we can just join those two things together. One thing worth noticing is that this picture has got very busy with all these annotations on it, and you might feel uncomfortable sort of having something quite as messy as that in an exam. So it becomes slightly problematic to know how do you actually document all of this stuff. And one thing that's worth doing, you know, which I haven't done here, but which we could have done, would be to just go through, and let's just change the color. Let's just say what you could have done is to label each of these peaks. So A, B, you know, C, D, E, F, G. And then instead of having to have all these annotations around the spectrum, you could just talk about, you know, peaks A and B have the aromatic shift, blah, blah, blah. You know, peak C disappears in D2O. And that's quite a neat way of writing the same information down without having to sort of fit it all in with lots of arrows around the spectrum and so on. Okay. So let's just put our two structures together. So this was the first bit we worked out, and we can now just add on our second bit that we've worked out, which is that we have CHOH attached to CH3, and that's our whole structure. Problem